Welcome back to the Foundry by Forge College. In today's explainer, we're taking the raw materials from our last lesson, those synchronization mechanics and patterns we talked about, and we are finally building a complete, cohesive architectural house. If you've ever found yourself wondering why Solana's Turbine protocol doesn't just use a simple single-file line to send its data, well, you are definitely in the right place. We're moving way beyond just looking at the individual pieces today. We're going to figure out exactly how to stack them together so they actually survive the absolute chaos of the wild internet.
Here is our quick roadmap for today. We'll start with the 3 blueprint layers of network design, then explore 2 totally distinct architectural patterns, ordered pipelined and parallel redundant. After that, we'll map out a 5-stage design workflow, and finally, wrap things up with how to actually validate your masterpiece.
All right, let's jump straight into section 1, the 3 blueprint layers, zoning laws of network design. Before we can even think about putting up balls in a roof, we really need to establish the foundational zoning laws of our network. So what exactly is a cohesive architecture pattern? Basically, it's a packaged set of responsibilities, synchronization techniques, and protocol interactions that solve a recurring data transfer problem. Think of it as your master blueprint. It stacks responsibilities vertically, ensuring that literally no component gets confused about whose job is whose. Because trust me, if the network drops a packet, everyone needs to know exactly who is responsible for catching that mistake and fixing it.
To make this a bit more concrete, imagine a 3-story building. Up on the top floor, we have the orchestration layer. This is the boss. It assigns tasks, decides the order of operations, and issues all the control signals. Down on the ground floor sits the transport layer. That's your delivery fleet. Its one and only job is moving data from point A to point B, maybe using some redundancy or retransmission to get it there. And finally, down below, we have the assurance layer. This is the basement crew doing quality control. They verify the delivery and reconcile any conflicting timelines. And let me tell you, absolutely nobody wants to be stuck in a windowless basement cleaning up a sloppy transport layer's mistakes. Now, when you choose a specific synchronization technique, you are essentially making a promise across all 3 floors of your building. If you use strict sequencing, the orchestration boss acts like a total dictator, issuing monotonic sequence IDs. Because the boss is so strict, the transport layer gets to just use a simple ordered forwarding path. And the basement crew, they get a wonderfully easy job, simple delta verification. They just check off numbers on a list, 1, 2, 3, and if 4 is missing, they just ask for 4. But if you use soft sequencing, where the boss is hands-off and just uses causal metadata, the transport fleet now has to use opportunistic multipath forwarding. And suddenly, the assurance layer has to do some serious heavy lifting with conflict resolution and merge rules. So you're always trading strict upfront control for a much heavier workload down in the basement.
Which brings us to section 2, pattern A, the ordered pipelined approach, strict but predictable.
Let's see how this actually builds into a real-world scenario. The core trade-off we always have to navigate here is predictable latency versus delivery resilience. Pattern A acts as a very strict assembly line designed for predictable latency. It wants everything orderly, fast, and exactly in sequence. On the flip side, we have Pattern B, which acts as a chaotic but highly resilient delivery swarm. Pattern B cares way more about the package surviving a hurricane than arriving in perfectly sequential order.
In pattern A, the orchestration layer acts like that strict boss we just talked about. A leader assigns exact sequence IDs to every single chunk of data and publishes a clear manifest. Because of this, the transport layer just follows a highly preferred forwarding tree, and the assurance layer has a delightfully trivial job, simply checking for missing numbers. It is incredibly efficient for reconciliation, keeping your CPU and memory usage nice and low. But here's the catch, especially for high-performance networks like Solana. If the leader crashes or even just one packet drops, the entire assembly line literally stalls until a new boss takes over. For global scale, it's just a bit too fragile.
And that perfectly transitions us to section 3, pattern B, parallel redundant streams. It's chaotic but incredibly resilient. This pattern is built for when network conditions get incredibly rough, or you care about absolute survival, not a polite assembly line. Here, the orchestration boss completely gives up on strict global sequences. Instead, they just tag data with causal metadata and fire it off. The transport layer goes into absolute overdrive, using aggressive redundancy and forward error correction, or FEC. And honestly, this is exactly the philosophy behind Solana's Turbine protocol. It actually burns bandwidth by shredding data and blasting it out over UDP to guarantee delivery, which completely forces the assurance layer to sweat it out and expend heavy CPU to piece the puzzle back together. You're purposefully trading bandwidth and computing power for extreme bulletproof resilience.
So you might be sitting there wondering, how do you actually decide between the strict predictability of pattern A and the intense resilience of something like Turbine? Whether you're hacking away on your own Forge College learning projects or designing core blockchain infrastructure for the real world, you can't exactly just flip a coin. You need a truly systematic approach to make this call. That is where Section 4 comes in, the 5-stage design workflow, otherwise known as the architect's checklist. To build that perfect cohesive network, we rely on a 5-stage workflow that forces a strict, logical progression. Stage 1 is requirements capture. This is where you define your acceptable tail latency and bandwidth overhead. Next is Stage 2, candidate mapping, where you map those goals directly to your techniques, like matching high loss tolerance with redundant parallel paths. Then Stage 3 is layering, literally assigning the boss, the fleet, and the basement crew their specific contracts. Stage 4 is failure mode specification, where you map out exactly what happens when a node drops or a leader outright crashes. And finally, Stage 5 is validation planning, defining the synthetic tests that actually prove your design works. Look, if you skip any of these stages, you aren't really designing an architecture. You're just crossing your fingers and hoping for the best. And that naturally brings us to Section 5, validating your masterpiece, the final inspection. Because let's be real, an architecture without concrete tests is just a hypothetical doodle on a napkin. Validation is absolutely crucial. You can have the most beautifully layered design in the world, but if it hasn't survived a simulated Byzantine node attack or a brutal 10% packet loss test, it is simply not ready for production. And the ultimate golden rule I want you to take away from this explainer is this: well-aligned responsibilities reduce emergent complexity. When your sequencing strictness at the top aligns perfectly with the reconciliation workload at the bottom, your system becomes predictable. And in network design, predictable is exactly what you want to be. To continue exploring advanced data transfer concepts, please go visit the website forge.college. We've got plenty more resources, deep dive courses, and learning materials from our team to help you master these exact systems. But right before you log off and go build your next cohesive Web3 system, I want you to ask yourself one final question. What unmapped failure mode is secretly waiting in the shadows to break your perfectly layered architecture? Think hard about that gap between your transport and assurance layers. Find it, test it, and fix it. Thanks for watching, and happy building.